Yes, sir.
Okay, sir. Thank you. Dear participants, good morning. The second session of day 3. I welcome Dr. Mohit Hemat Kumar, who has completed his M.Tech from CEG campus of Anna University, completed his PhD from NIT Tiruchirappalli. Also, he completed his postdoctoral research from King Mongoose University from North Bangkok. Moreover, the expert of Dr. Mohit, he has published more than 20 research articles in international peer-reviewed journals. He also published more than 5 book chapters and editor of a book. In his research area, he has received 2 patents and 8 industrial designs from IPR. Currently, he is working in different fields which include natural fiber and inorganic fillers-based polymer nanocomposites, metal matrix composites, and based on innovative industrial product design. On behalf of IIIT Tiruchirappalli and the participants of this faculty development program, I welcome Dr. Mohit Hemat Kumar for sharing his knowledge. Welcome, sir.
Thank you so much, sir. I will share my screen now. So I would like to present. So today I am going to present about a topic that is pillars-based polymer nanocomposites for different engineering applications. So currently I am working as assistant professor in the Department of Mechanical Engineering, Alliance College of Engineering and Design, Alliance University, Bangalore, Karnataka. So what about, before going to a topic, first of all, we should know what is pillars. So pillars can be any type, and which can be made up of either natural or inorganic. So why we are using a pillar material here? Because it's like a type of reinforcement material for the enhancement of properties in the polymer composites. That means polymer is the major material in types of composites. So these type of pillars can be acquired from different sources of field, like even from waste or from any other non-renewable sources, like in terms of fly ash. So this can be used as a reinforcement material to the polymers in order to enhance the different properties of a material, like mechanical properties, thermal properties, or physical properties, or any other electromagnetic shielding properties. So depend upon the filler which we are using for our composites. So according to that, we can apply for different engineering applications. So before going to that detail about the topic, first we should know what is composite. So composite is nothing but it's a combination of 2 or more substances with significantly a different physical and mechanical property or chemical property under a macro scale. So even we can say it's a nano scale or a micro scale. So the discontinuous phase, we can say as a reinforcement, either which is generally harder or stronger than the continuous phase, which is applied in terms of reinforcement. So whereas a continuous phase is called as matrix. So that's why we are telling as a matrix the major part of a composite, which having highest content of ranging from 60 to 80%, or till we can use it 90% also we can use it. So depend upon the material of the matrix, we can share into 3 types. First one is your polymer matrix, then metallic or even ceramic matrix. So that means in this condition, what we can see that polymer is a major one, whereas metal is a major one, another one is a ceramic is a major one. So in recent years, we have observed that polymers substituted in many of the traditional materials for different applications instead of metals. Because why we are not using metals? Because metals having higher density than the polymers. So if you use polymers, you should have a low cost and productivity and ease of processing will be very less. So one more thing is that, so even the last 50 years, people have switched over to the plastics based composites and ceramic based composites, which is the ceramic and the plastics are combined together to form a different advanced material in composites, which are mainly dependent upon the emerging materials in the field of market scenario. So now the composite material is classified in 6 different types as particulate, fibrous.
Sir, hello.
Yeah.
Sir, Professor.
Yes, sir. Yes,
Sir,
sir.
your slide not visible, sir.
Slide not visible.
Ah, yes, sir. So your presenting screen not visible, sir.
Okay. Is it visible now? My share screen is.
Oh, sir.
I think sorry an error has occurred when sharing like this sharing. Please see dismiss again. Stop sharing and share the entire screen. This one. Is it sharing now?
Yeah, now it's working, sir.
Okay. Okay. Is my presentation is visible to you?
Yes.
Yes, sir. It's visible.
Okay. So now we are going to composite material. That means we have different types of composite material depend upon the size or structure. So generally we can divide as composite material in terms of particulate reinforced, fibrous reinforced, and another type we can say as polymer based, metal matrix based, or ceramic based, or carbon based. So these are different types which can be classified the composite material in different ways. So this is a general type we have discussed. So before going to in depth, what we can say first is particulate matrix composite. So particulate, from the name itself, it shows the reinforcement of the particles or platelets, either which in the shape of the cubical or spherical form, that is what tetrahedral form, or any other regular or irregular shape, which can be dispersed in all directions. Okay, and the main advantage of this type of composites, which can increase different properties of materials like thermal performance under very higher temperature, depend upon, like we are using particles as ceramic material. Some ceramic having silicon carbide, titanium carbide, we have used. We are reinforcing around it's having the melting point around 3500 degrees Celsius. So it will improve the thermal performance of that polymer composite if you reach that, reinforce the particles in that. So even we can reduce the shrinkage during the fabrication process, and hardness also be improved. So next one is your fibrous composite. So fibrous composite is being characterized with the fibers which is extracted from either from the natural resources or any other different types of plastics. So it's having a higher cross section when compared to the other dimensions of the fibers. So why we are using fibers? Because fibers can also be used for increasing the fracture resistance of the polymers. So if you have long fibers, your fracture resistance of the polymer or resin will get improved. It depends upon the volume fraction and the weight fraction, which we are going to reinforce in the composite polymer matrix composites. So the fibers which having the smaller dimension, so this is not at all suitable for applying the engineering application. Because why is so? Because it will affect randomly oriented. So what will happen? The material will get an anisotropic property. So that's why we are not using smaller cross-section dimensions instead of using a larger one. So another process is that, so if you create a good binding between the fibers and the matrix, we should shift the loads to the fiber, and which should be protected from the damage and environment. Why we are using polymer matrix composite? Because it is free from the corrosion resistance, so it will not affect the damage. So another thing is that the fiber will bind with the polymer in order to give the strength to the polymer matrix, and which will protect from the damage even from the environmental attack. So another thing is that, so the load transfer function of the polymer is more critical than the long fiber composites in terms of, if you compare with the short fiber reinforced composites. So now we are going to different types of depending on the matrix. First one is your polymer matrix composites. So polymer matrix composite is nothing but it consists of a resin, either thermoplastic or the thermoset, which can be either reinforced with synthetic fibers or plant fibers in a dispersion medium. Okay, so these are the what are the advantages of this using this polymer matrix composites? Why we are using? Because for higher strength, lower cost, and easy to manufacturing and fabrication of the process. So major drawbacks of these composites, they have very higher coefficient of thermal and moisture expansion, and lower operating temperature with a lower elasticity of properties in specific directions. So for this condition, if you use a ceramic material or metal material, it will even just remove this major drawbacks of these composites. So now we are going for metal matrix composite. So in this case, we have magnesium, aluminum, titanium, which is concerning a typical fiber reinforced with silicon carbide or titanium carbide or carbon in order to improve the wear resistant properties and thermal conductivity of the material. Okay, so how the metals has been designed is to reduce the or increase the property, it depends upon our requirement. For this case, the thermal conductivity of the material can be increased with the addition of the ceramic fibers, like because ceramic fiber like titanium oxide or SiO2, if you add that one, the thermal conductivity of the material will get reduced. If you want to improve the thermal expansion, we can reinforce the silicon carbide, titanium carbide, and the strength and stiffness of the material can also be improved in the metal matrix composites. So now we are going to ceramic matrix composite. So the ceramic matrix composite having the major part is the ceramics, like either silicon carbide or calcium aluminum silicate or aluminium. And why we are using this type of composites? We want the material should be higher hardness, a lower density, but we should have a higher surface temperature for during the process. Another thing is that we have carbon-carbon composites. So the carbon-carbon composites, it's depend upon the matrix is used as a carbon. So in this case, these type of composites are applied in very high temperature environments, and even they are 20 times stronger than the graphite fibers, and which are 30% lesser than the already conventional materials. So what is the advantage of these composite sides? So we have like lower density, higher fatigue resistance, we have higher mechanical and thermal properties, and finally the drawback is the higher cost, because the fabrication cost will be high and higher oxidation under different range of temperatures, and the shear strength will not that much capable to perform the things. So now we are going to the polymer nano composites. Okay, so what we are going to do is we are going to reinforce the inorganic or organic or natural fillers in the polymers in order to fabricate the advanced type of plastics. So this can be designed in terms of processing the selection of the inorganic particle which can be applicable for our requirement. So for example, if you are using silicon carbide or titanium carbide with the natural fiber composite, it's like it will be called as a hybrid natural and metal ceramic based composites. So in that, what will happen? Your property of the material will get improved. So another thing is that reinforcing elements should be always in the nano form in order to get that uniform dispersion within the matrix. So another thing is that if you have reinforcing the nanofillers, which offers higher properties than the microfillers, because the dispersion capacity is very high due to the smaller aspect ratio when compared with the micro particle reinforcement. So another thing is that with utilization of these nanoparticles, it will offers you different types of new properties, like we can produce improvement in the inflammability property and reduction in the swellability, and the highest strength will be obtained. So now, if you are using polymer composites and in its blends means the combination of two resins. That means one resin, for example, if I am saying one resin is epoxy, it is mixed with your silicon carbide, and another resin is mixed with your polyester mixed with your titanium carbide. So this can be, while fabricating the process, these can be blended with each other to fabricate a composite. So how it can be fabricated? First, you have to, in the hand layup method or any other process, first you have to mix the epoxy and silicon carbide in the same platform. Then another thing, you have to mix the polyester and then after over it. So this totally concept is called as blend. So this type of blends can be used as an alternative material for the conventional polymers. Okay, so now we have this immense nanoscopic dimension, whereas the interfacial area which between the nano elements which differentiate the polymer composites from the traditional composites. So the dinostopic dimension of the area which is used for the reinforcement of and the fabrication of polymer nano composite, which is completely different from the conventional composites. So conventional composites, what is that? We are just mixing the filler like any natural fiber, or we are mixing any organic fiber, singly we are mixing. But that is a micro form. But in nano composite, we are mixing both the things in nano form in order to get the good dispersion, and you will to get even distribution of the both the plant and natural fiber. So by considering this property, we are seeing that they are generally compared with the traditional and unfilled polymer. So which is, whereas this condition is not at all correlated with the continuous, that means the long fiber composites. So another thing is that traditionally we have, another thing is that among the different types of multifunctional materials, so the first point is they have the higher mechanical properties as per the desired condition. The second one is the performance and the cost will be very more. Then if you are going to next part, that's how the multi-component materials has involved either nanoscale or microscale by which is completely dependent upon the four areas. That is the first is your selection of the constituent. That means, for example, if you are using a metal matrix composite in the polymers, for example, if you are using aluminum or silicon carbide in the same composite in the polymer as a nanomaterial, why we are using that one? Because we can get to a higher thermal stability to improve the mechanical and thermal properties. Okay. Another thing is the performance. Which I told you, the fabrication method. How we are going to fabricate the polymer composite. Then processing of that multi-component. So before reinforcing with the multi-component, what first we have to do is we have to go for the ball milling process, the mechanical alloying process, in order to reduce the size of the material and in order to mix the uniformly within that particular matrix. So that is also one of the factor during the fabrication of polymer nanocomposites. So what are the properties? So as we already told that nanoparticles can enhance the rigidity and stiffness of the polymers. So without affecting their toughness and elongation. So if you have higher aspect ratio and smaller size, substantially your mechanical thermal property will get improved up to 10%. If you mix more than that, what will happen? Your nanoparticles get agglomerated and accumulation will form, and certain positions, the anisotropic material will be characteristics will be produced. So that's why, not to avoid that one. So we are, as per the different research studies from different scientists from the world, they have achieved that up to 4% we can go for the very smaller particle size and a higher aspect ratio. So another thing is that the lower concentration even disperse quickly, and which also maintains and controls the better transparency than the traditional reinforcements. So depend upon the type of the nanofiller which we are using, that also is one of the factor for improving the mechanical and higher thermal characteristics, and which also produce a lower density material. Okay. So for example, if you are seeing there is a nanofiller applied in the finished product, and which is in the range of 50 to 150 nanometer, it's having diameter. So whereas the aspect ratio is very, very high. So what will happen from this case, if you put a lower concentration of filler to the polymer or any other metal or ceramic, what will happen? Your conventional material will get lower property than this when we compare to this a new product. Okay. So the percolation threshold of this composite should be less than half of the 1% when compared with the volume. So another thing is that the nanoparticle applies in this process is because we have tons and tons of nanoparticles we have available in this world. So in order to provide a realistic and affordable scale in order to get the resultant polymer based nanocomposites. So that's why we are using a nanofiller as a material from the different types of tons of quantity in order to depend upon the improvement of the properties of the mechanical and thermal properties. So how this nanocomposites is compared with metal fill systems which offered substantial flexibility, weight saving, durability, low temperature processability. So now other thing we have, so many researchers, these type of nano pillars can also be used as a for the manufacturing of the paints, coatings or sealants or any other tubes, which can also be applied as an electromagnetic shielding for different structural purposes. Okay. So now what are the challenges in processing the polymer matrix nanocomposite? So first is in order to make this challenge, it should be a practical innovation is very tough. How? It's because it's a risk factor, because the content is very toxicology, and it's regulative because it's not because we should use the method efficiently in order to manage the things, because it's a nanoparticle. Even if it will go in your while processing, it will go in your hand, and we don't know how it came in our hand. If you're eating something, it will go to our mouth and it will go to our stomach also. So because it's very toxic, so it will limits the bio-nano manufacturing materials. So in order to avoid this one, so we are using a bio-based nanomaterials, which can be applied as a reinforcement of the polymer nanocomposite with different types of processing methods. So another thing is that the efficiency of recycling and reusing the bio nanoparticles, which can be easily synthesized, in the future can also be considered. Like the bio nanoparticles means we are considering from the bio-based polymers or from the bio-based plants like the pillars like that. So we are getting the bio nanomaterials from that, and which can be considered, which improves the efficiency of the reusing and recycling of the composites. So another thing is that for producing these type of nanoparticles, we should reduce the energy requirement, or also optimize the energy waste, which is raised during the elimination of this biotechnology implementation. So another thing, so for the last point, by developing sufficient plant, so this design with lower energy requirements can be significant problem when pursuing the nano production methods. Okay, so these are the different factors, the factors for affecting the performance of polymer nanocomposites. So first one is your type of the pillar which you are using. So type of pillar is, as I have told you earlier, that is either swellam, or either it can be a natural pillar or is a synthetic pillar or metal pillar. So another thing is selection of the material matrix. So selection of matrix is based upon what type of material we are going to use in our application. For example, if you want to use a material as a recyclable, so you can go with the thermoplastics. If you want to use as a permanent one, you can go with the thermosets. For example, nowadays, even biodegradable study also is there. So people have switched over to epoxy, pure epoxy. They have switched over to the new type of epoxy, like bioepoxy. So bioepoxy, like we have bioepoxy SR56 and SR33. So these are different types of bioepoxy which is available in the market. So this can also be used as a polymer for biodegradable studies, and which can be easily biodegradable when compared to the conventional epoxy like L556 and the other bisphenol A like that. So the one more thing is the interfacial strength, how the bonding between the pillar and the matrix has been matched. That is the interfacial strength. So and then what is the dispersion of the pillar? So how we are going to disperse the pillar, because these are the very small particles that we can say that is called nanopillars. So how to get the dispersion of these pillars? So another thing is the orientation of pillars. That means what is the size of the pillars, what is the diameter of the pillars. So depend upon the structure of the pillars, we have to select what type of performance we are needing for in order to improve the polymer nanocomposite for different applications. So another processing we have like a manufacturing process. So manufacturing process is about the fabrication technique of fabricating the polymer nanocomposite, which is combined with the a conventional one. Like we have filament winding process, we have spin screw extruder winding process, the compression molding process, so, and hand lathe method. So we are just making the things by including the nano processing methods, and we are using the same conventional things by using the fabrication process. The another thing is a porosity. The porosity is about that means the porosity of the natural pillars. It's not about the metallic pillars, because porosity is only from the natural pillars because they have more moisture content in that. So how to avoid that? So before, so we have to go for the furnace heat treatment at 80 degrees Celsius for 24 hours in order to remove all the moisture content. Then that can be mixed with the polymers in order to get the good performance of the polymer nanocomposites. So as I told you, there are different types of pillars. So first one is your natural pillars, which we can say are plant-based, and second one is animal-based, and third one is your agricultural-based. And for the synthetic fillers, we have 4 types. That is, we have ceramic particles, carbon-based materials like carbon dots, CNT, and graphene. For metal oxide particle, like we have TiO2, SiO2, like that we have. The metal particle, like we have magnesium, aluminium, like that we have. So now, so before going to the detailed manner, first I will tell you what is the plant cellulose fiber. So plant cellulose fiber means it's having a one type of filler which is divided into 7 categories. Okay, so depending upon seed, we have 2 categories that is called cotton and kapok, and another depend upon the, this is 7 category. How they decide 7 category? This is completely depend upon the structure of the plant. That is, this one is type of seed, and there is bast, then leaf, then wood, then fruit, then stalk, then depend upon the grass or reed. So there are different types of different fibers in the plants. This can be acted as a fillers. So fiber means the length should be more than 1 millimeter. If you are selling fillers, it should be either in micron or in the nanoparticles. That is called fillers. Okay. So how to extract these type of filler from the plant? So there are 2 types of fabrication method. That means we can say surface modification method. Other we can say surface treatment method. We can say the first one is your chemical, another one is your physical. So chemical having gamma, plasma, and corona and ultraviolet, whereas the chemical treatment having alkaline treatment, acetylation treatment, then benzylation. So there are different types of chemical treatments which can be used for the removal of lignin particles and hemicellulose particles. So we cannot able to remove all the particles from the system. So first we are doing alkaline treatment. Alkaline treatment we are doing with the help of NaOH. So if you are using more NaOH, what will happen? For example, if you are using 1 normal D or 2 normal D, what will happen? Your cellulose structure will get damaged. Even the lignin will remove, the cellulose structure will get damaged. And if your cellulose structure will get damaged, means you are not able to get the desired property of your composites. Even if it's in the form of a nano form or micro form, because the concentration of that cellulose content will get damaged. That is the main thing. So depends. So everything having a optimum concentration, which is available through all the net. That is, we have, for example, alkaline treatment. If you go, we can see it's a 0.1 N NaOH. Okay, and some people what they are doing this 0.1 N NaOH for boiling the water temperature and for 4 hours. Some people doing in the terms of just soaking and keeping out. So these are different types of chemical treatment. So even we can do in the boiling temperature, also we can do in the form of just soaking out for some time period, and we can remove it. And after removing this, we should be washed with deionized water in order to get that fiber concentration correctly. Okay. So now we are going to nanomaterials. So what is nanomaterials? So there are 4 types of nanomaterials. First is your 0-dimensional, then 1-dimensional, then 2-dimensional, and 3-dimensional. So if you see this one slide, this is called 0-dimensional. So in 0-dimensional, we have a particle called zinc oxide. So zinc oxide is completely merged with each other to form an element zinc and oxygen, which is completely merged with each other to form a zinc oxide. And this is there is no dimension of this nanoparticle. That means the powder is only in the powder form, but there is no, we are not able to measure what is the dimension, what is the diameter, what is the length, we cannot able to measure. But in terms of CNT, we can measure there's a 1-dimensional, we can measure what is the diameter of the CNT. Okay, so this energy graph will show you from energy obtained up to the Gibbs energy. From this, it's going in a stable manner. So there is no dimension occurred during the synthesis of zinc oxide. But in CNT, what happened? Sudden that energy has reduced, and it will only the single dimension has been enabled in the CNT. So that's why we are saying not a diameter of the CNT. So for the graphene sheets, you can see this one. That means we can get 2 spaces is there. So that's why we are getting 2-dimensional. Then the polycrystal like the same there. So now, what do you mean by dispersion strengthening? So dispersion strengthening is the one type of mechanism. So how the dispersion is being mixed and reinforce. What is the fact that dispersion is one of the factor which can be helpful to reinforce the things within the polymer, because polymers have been lower viscosity. What will happen if you mix during the processing, your polymer will get lots of bubbles actually if you mix with the mechanical stirrer or any other stirrers. So in order to avoid that one, we are dispersing the particles in uniformly with the help of probe. So this is called dispersion strengthening. So from this 6 graphs, that is same image, you can see there is a small spot dispersion and different micro images. That is, we can say this point micrometer. You can see there is a dispersion of the nanoparticle with each other, but even small gaps are there. But this is not 100% dispersion. So if you see in the 20 micrometer, it can be seen that there is 100% dispersion of the nanoparticle. So this is different. So this is the one type of method. Hello. Yeah. Okay. So this is the one type of method to strengthen the bonding between the particle and the polymers. So these red types are the polymers which attract and bond with each other with the atoms that are our nanoparticle atom, which bind together to produce a strength and connection with interconnect with each other to give a good performance while during the testing process. Okay. So as I told you, so we have a mechanical alloying method. Okay. So there are different types of mechanical alloying. First is your horizontal type of ball mill, then vertical type of ball mill, planetary ball mill. So in that different case of ball mills, so balls to powder ratio is the one of the factor which plays a major role during the fabrication of this mechanical alloying, the fabrication of this nanoparticles or the mechanical alloying process. For example, if some people are using 6:1, and if you use 10:1, the 10:1 will be the higher performance for reducing the particle size, and it can evenly mix the particles with each other. So this is the ball milling process. The balls will rotate, and from this, why we are using balls? Because this point is having and every 360 degree it will attack the our particles. Okay, and it will break and it will mix. So that's why we are using the mechanical alloying process in order to make the synthesis of the nanoparticles. So this is one of the method for dispersing of metal to metal or ceramic to ceramic or metal to ceramic or metal to carbon or different types of metals by using a ball milling process. So now how the system has been dispersed. So because it's a nanoparticle, as I told you, we cannot mix by using hand, or we cannot mix by mechanical stirring process. So this is one type. So there are two types of methods. We can say ultrasonication process. So in that two types, we have one type is ultrasonic probe, another one is ultrasonic bath. So in the ultrasonic probe, it's a probe. This is called probe. This probe is having a small. This probe will create an ultrasonication waves by using a control unit at around a maximum of 24 megahertz of power supply. 24 megahertz of power supply. And what is the steering speed? And from that from that ultrasonic waves, the particles are dispersed evenly within the polymers. So this yellow is the polymer. Okay, if you put some black one, for example, if you're putting some black like carbon, if you're putting or graphite, you are putting. So what will happen? You should put up to 4%. Then the sonication time should be minimum 2 hours. Okay, so that 2 hours will disperse the particle evenly within the matrix. But it is not. We cannot sure that this is 100% dispersion. This is only for 90. Even we can say it's 90% dispersion. But while seeing in the semi samples, if you see, there will not be a single. We will not get a uniform dispersion. So this method can be used as for the nanoparticle for the dispersion of the particle when compared with the other conventional materials like mechanical stirring and hand stirring. But another thing is that ultrasonic bath, the same principle by using a hot water bath we are doing. But the efficient one, if you say, it's a ultrasonic probe is the efficient one, which is people are using recently nowadays. So, how the particles have been distributed? When we have sent them the same image, you can see. So, these are the nanoparticles, which we can say it's an even distribution of nanoparticles. Okay. So, now if you go to the B part, so what does it mean? It's a random distribution of the nanoparticles. And finally, we have the C part, that is, we can say agglomerated concept. Okay. So, degree of variability between the sub areas is depend upon the lower size to the higher size. Okay, so if you give, if you, for example, if you are doing in a lower speed, then dispersion will be very high. But that dispersion will be very high, and if your time has been reduced, then what will happen? Your dispersion will again attack with each other. Okay, so this polymer should be, for example, if you are using epoxy. For epoxy, we are using hardener. Okay, so hardener having the curing time for at least 2 hours. Okay, but if in polyester, this is not possible, because polyester, if you add accelerator and catalyst, after adding catalyst, your curing time will be within 5 minutes. So before that, what we have to do in the case of polyester, for 2 hours, you have to mix the resin and accelerator the same time, and you have to disperse the nanoparticle in the polyester while pouring into the, if you want to shift or if you want to make the sample, finally you have to mix the catalyst and then you pour it suddenly. That's the difference between a vinyl ester, polyester and what is that? Epoxy. So vinyl ester and polyester having the same logic, whereas epoxy have a different logic. But this is for epoxy, we can say as a ratio of for epoxy, if you are using L by 5/6, we can put the hardener ratio in the ratio of 10:1. That is, we can say 10:1. But in hardener, for example, if you are using in polyester and vinyl ester, we can put in vinyl ester we have 3 components. That is called resin, promoter, accelerator, and catalyst. So promoter, accelerator, and catalyst should be 2%. But in polyester, we have accelerator and catalyst, we have 2%. But if you compare these things with bioepoxy, like SR56 or SR33, so in that, what will happen? Your hardener ratio, mixing ratio is more than the previous one. For example, epoxy convention having 10:1. For FR56, we have 33 is there. For SR33, we have 64:36% is there. That is the ratio for hardener and bioepoxy based, and this one. If you compare even between this SR56 and SR33, we can say that SR33 is better than the SR56. Why is it so? Because SR56 having the low carbon content, whereas SR33 is having the highest carbon content, which is completely obtained from the vegetable parts. Okay, so this is another thing. That is, we have particles. Okay, how the particles has been aggregated in the form of, but this is aggregated form of particles during the process of ball milling or any other mixing process. If you are saying agglomerated. So agglomerated means just due to higher speed and lower time, what will happen? These total particles will get attacked with each other, and they will form a large particles. Okay, so this is called agglomeration. So we can say there are 2 different. First, we have in stable suspension. It means we have even distribution of the nanoparticles within the matrix. Whereas in unstable suspension, we have 2 stages. First one is your early stage. That means while doing the process, what will happen? Your particles will get rotated at the edges of that cylinder. But after the later stage, what will happen? Your particles will get attacked with each other, and it will form a gels with each other. It will get interconnected and it will connect like this. So this is one type of called unstable suspension. Okay, so there is no proper suspension between the matrix. So this can be happen in ultrasonic bath, and we can get it from the ultrasonic probe. Okay, so now, so how this nanoparticle has been dispersed? By using a dispersant. But in nanoparticles, for example, if you are using ultrasonic bath, we are using a dispersant particle. Okay, which will attract the ion content with each other due to electric repulsive force. what will happen? Your dispersion has been taken place and agglomeration will occur when compared with the ultrasonic probe logic. Okay, so what are defects we are getting? So for nanoparticles, if you see that different types of defects we have, that is vacancies, interstitials, and interstices, and discordant atoms. So this is called for two-dimensional. This is for two-dimensional defects. And for one-dimensional defects, we have a dislocation of the atoms with each other. And then two-dimensional, there is a ground. There will be, we can say, there is a grain boundary or a twin boundary of stacking faults. So while attaching with each other, like in the graphene sheets, what will happen? The boundary of the material, that the graphene sheet will get reduced, or it will not get any uniform size. That is the thing. But in three-dimensional, there is a formation of the voids, more number of voids, like we can say porosity, and also there is the production of the nanoprecipitate on the surface of the during the processing of nanoparticles. Okay, so now this is one type of defect. We can say if you put sonication product, so what will happen? Your particles will get attacked with each other. Okay, and which is called molybdenum, which is having lots of defects, like where there is no proper connection with each other, and lots of voids have been formed in between the atoms. Okay, but in if you're using an antioxidant during the sonication process, this is completely occur in our ultrasonic path only. So in that process, what will happen? A small chain will occur with each other, and they are interconnected and produces the electrical pulse within the. So that's why we are killing. This is a defect-free molybdenum sulfide. Okay. So now, so how the nanoparticles have been fabricated? Okay, there are different types of fabrication methods. So we can say this is like that. We can say chemical synthesis, electrochemical deposition, electrode deposition, then chemical vapor deposition, then physical vapor deposition, the SolGel method, and electron beam lithography and template method. So now this is called your chemical synthesis. By using a magnetic bead and magnetic stirrer process, a stabilizing agent has been produced inside that with the precursor of nanoparticle. Okay, at some temperature and pressure and higher the speed, when the lower speed, what will happen during the chemical processing? Your chemical nanoparticle has been produced. Okay, with the help of magnetic stirring process. The second one is your electrochemical deposition. So in the electrochemical deposition, what happened? It's like an coating the one metal to another metal, like cathode to anode. So first what will happen, the metal deposit has been generated at the anode side. This particles like cations or surfactants as absorbed on the different layers, like first we have the stage, that diffusion layer, that this diffusion has taken place and which is converted into convection layer. Then finally the convection layer is dispersed in the form of bulk electrolyte. That means the metals like the atoms of which are connected with each other, whenever that deposit, it will in three different layers. It will, due to the electrochemical reaction, what will happen? It will get dispersed with each other, and the bulk electrolyte has been formed, which has been soaked inside the. Okay, so next one is your electroless deposition method. So in electroless deposition method, we have depositing the electrode. That means we are depositing the electron ions. That means this is a ceramic particle, that is alumina, and this is your silica. By using the effect of OH and NH2, okay, we are getting a surface sensitized on the ceramic with the help of the tin ions, and this has been converted in the form of leads. Okay, that lead has been removed and electron has been deposited on the substrate. Okay. So from this we will get the silver, like we have using from coating the one part to another part method. Okay, so now we are going for chemical deposition method. So in a chemical deposition method, having a setup called flow controller, whereas the initiator and monomer has been controlled with the help of a valve, and which is passed through the vacuum chamber. And this roller, what it does, the initiator and monomer, that monomer will flow on that vacuum, will be flowed on that tubes. That particles has been deposited in the form of vapors, and the exhaust has been removed. So that particles has been segregated with terms of a collector. So this is called vapor chemical vapor deposition method, which is completely happened in the stage of maximum 50 degrees Celsius, and physical vapor deposition method. So what we are doing is, so we have created a substrate and which is completely hold with the substrate holder, and we are giving a sputtering gas, that we are giving a plasma ion gas we are giving, like in terms of inert air gas, that we can say it's RN gas we can say. Okay, and sputter atoms has been developed with the help of a growing film, and from this case a HAP target has been removed. That means a heavy alloy target has been removed, and this is completely a vacuum chamber. From this, particles has been deposited, the nanoparticles deposited on the highest on this disc, and with the help of the vacuum. Okay, so now the SolGel method. So in SolGel method, we are mixing the precursor with the solvents. Okay, so then what will happen after mixing? The sol has been formed, that is the colloidal structures has been formed, which are connected with each other. And then now we have divided into three terms. But first one is your supercritical drying, then thermal drying, then freeze drying. So in this three types of aging and drying process, we are getting aerogel, zerogel, and cryogel. This actually we will get in the form of a small liquid which having some moisture content. So what we are doing is calcination process we are doing in order to get the powder. So that calcination process will reduce the size of the material which is already mixed in the form of precursor and solvents. Okay, the calcination process will be occurred in different temperatures like 600 degrees Celsius, 800 degrees Celsius, like that. Okay, so now we have electro beam lithography method. So from this we have this setup. This is a side view of that electro beam lithography method. So in that you see there is an electron beam source has been passed to the first condenser, and this has been condensed with the, we are using the beam blanket. Then again it is focused with another electron with the other condensing lens. Then with the alpha aperture, the size of the beam has been reduced and deflected, which is completely focused on the final condensed lens in order to create a small electron beam that means should be focused on a particular point. This substrate has been drawn on the surface of a material, that this small holes has been generated on this metal substrate. What will happen? Your metal will get a small powder pieces will get, that is in the form of nano form. Okay, so now a template method. So in the template method we have a formation of the micelles. This is called we have mixed a liquid solution of surfactant and the metal precursors, okay, with together to form a micelle forms. The micelle is a different type of at a higher concentration. That means we are mixing a chemical liquid surfactant with each other in the terms of atoms, and this has been shaped in the form of spherical rod. And now finally they have converted into the form of precursor called liquid precursor, that is called benzene, the type of benzene. Then aging has been occurred. Finally calcination occurred in order to find the copper oxide nanoparticles. So this is one type of method for producing a nanoparticle. So what are the different types of fabricating the polymer based nanocomposites? So as I already told you, so we have, this is already known process, a conventional process, but in the resin bath. Okay, what we are going to do is we are going to put some resin, either bioepoxy or epoxy or polyester or any other polymer matrix. Just this, like, it should be liquid. It should not be in the form of like solids. So what it will do? So these are the different type of threads. Either we can use this natural fiber thread. Okay, this natural fiber thread having different reels which have continuous threads. Either is going to first, what it will do? It will go to the resin bath, is soaked. All the natural particles with the resin mixture has been soaked and covered with this fiber, which is now passed to the rollers and then is guided with the rotating mantle. So this type of filament winding process has been used mainly for the purpose of creating the hollow cylindrical structures. Okay, so even we have studied, like for example, if we have nowadays what we happen, we are not able to get the natural fiber that amount of length, because if we want to wind this mantle, we need at least we need actually 10,000 meters. We need, okay, that is 10 kilometers we need if we want to get the mantle. So if you want that much of fiber, continuous fiber, the natural fiber will not give that much. So that's why what we are using, we are converting that fiber, that is our natural fiber, that we can say any other sisal fiber or hemp fiber or any other natural fiber. We are converting that fibers in the form of nano form, and that nanofiber is even combined with the ceramic or metal materials. They are being ball milled, okay. Then during the ball mill process, they are completely mixed with each other, and then some size has been reduced. Then after that, that ball milled material is combinedly mixed with the resin, okay, with the help of ultrasonic probe. That after the curing process, what we are doing is, we are just putting the resin, the resin mixture in the resin bath. Then a carbon fiber or glass fiber will roll, and you will get a hybrid polymer matrix nanocomposite, which can be applied in our different applications, for piping applications, or any other tube and pipe heat exchanger applications. So these are different types of methods for creating a hybrid based polymer nanocomposites by reinforcing a synthetic fiber and also a natural filler or inorganic filler to get the good strength, highest thermal stability, and any other, like if you are putting TIC in resin bath, what will happen? Your electromagnetic shielding property will improve. So these are different types of method. One of the method for fabricating a cylindrical component, hollow cylindrical component using a mandrel. And this is one type of setup. So even this setup can be, you can say, even this setup can be even coupled with lathe machine also. So in lathe machine, what we can do is, we have the chuck part, we can just place the mandrel, and in the tool post at the guide bay, we are using for, and the tail stalk, we are giving that a tool post. We are taking the resin bath, the same roller will come and it will wind the things. And in the next part, in the tail stalk spindle, the fibers will come up. So this is one type of method we have tried. So this is also success. So we have used for glass fiber reinforced polymer composites, and also we have tried for cotton-based polymer composites. So now this is, we can say, autoclave forming. So autoclave forming having different components, as we have airflow inlet, then mold, the mold which we want to fabricate, then the outer wall. This is called outer wall. Okay, then panel where the component has been fabricated. So what will happen? A particular die has been placed inside the forming machine, and the same concept which I told you previously, that we are mixing the polymer matrix with fillers like natural and hybrid fillers, and even we are layering that carbon fiber layer sheets. Okay, from that we can manufacture different types of manifolds which can be lighter in weight and also having higher efficiency. So, so another part is your twin screw extrusion process. So this is one of the method for mixing only the thermoplastic materials. This is not applicable for thermosets. Okay. So what it will do from this we can say this is a twin screw extruder. This is a cross section of this equipment. So in this, the hopper, we have poured some PLA or PVA or PVC materials. This is in the form of crystals. Okay. And what it will do, it will melt and it will combine and it will come in the form of the wires. Okay. So this is, we can say, blending method. Okay. So not only we are mixing the PLA, even we can mix the PLA with coir fiber or any other natural fiber or any other inorganic filler. But the screw should be less than, because what it can do, For example, if, because we have a setup in that Thailand University, we can mix both the combinations up to 4% only. Otherwise, what will happen? Your fiber and your inorganic filler will get burned easily, and will not get give the proper mixing between the two things. So after getting the wires, we are getting the filaments. That filament can be used as a can be used for 3D printing for applications. Otherwise, we can chop that filament to the small particles, and that chopped fibers can also be used for your compression molding process and any other applications. Okay. So now this is one of the type called plastic extrusion method. So here this is the same principle which you have seen. It's like we can say it's a twin screw extrusion process. The same process here also happening. So in this case, instead of wires, we are getting a sheets. So what we are going to do is in this hopper, we are going to mix the natural filler or polymer like PLA or PVC or like PVA and some inorganic fillers. So what will happen? It will condense, it will mix, it will blend, and it will pass to the form of wires. And that wires is being converted into the form of sheet. And this sheet will be can be easily used for your any other applications like thermoforming applications. So this can be used for thermoforming applications like vacuum forming process. So this is the next step, as I told you, thermoforming process. So this is your mold, and after fabricating that, for example, if you are using with the PVC, okay, then this red one is nothing but it's your plastic sheet, which is developed from this plastic sheet extrusion process with the help of that inorganic filler and natural fiber. Then what will happen? From the top, when heat was there, it will heat this fiber of this plastic sheet, and the mold has been pushed up, and a small vacuum has been drawn in this part. Okay, and you can get a desired shape even using the polymer matrix composites with reinforced with this inorganic and natural fibers. Okay, so now as we saw, this is the different types of 3D printing process as I told you earlier, like stereolithography, then SLS, then SDM, then FDM. So this can also be used for that, as I told you, but this is for creation of that filament wires. That filament wires can be used in our different applications for the development of the polymer composites. So now we are going to testing methods for checking how the performance of our machine, that means the fabricated composite, has been improved. So for that, we have considered different types of tests. That is, we can say for mechanical property, we have compression test, tensile test, flexural test, and impact hardness. These are generally done by everyone. For polymers, as I told, I will tell you what are the standards. This one is for ASTM. We can use either 3039, otherwise we can use C638, D638. Okay, otherwise for this one for compression test, we can use 695. For flexural test, D790. For impact test, that we can say D256. For hardness test, we can use either show hardness A, or we should use only the show hardness D, because in show hardness D, the highest hardness will be there, because if you are using show hardness A, it is completely used for your elastomers and rubbers. But in show hardness D, it is only used for your polymers reinforced with inorganic filler and natural fiber, because the range of that hardness will be higher. For example, if you are using mistakenly, if you are using show hardness A, if it shows that time it's a 90 means, that means your hard intended is not at all okay for this hardness test for polymers. But you should change the indenter, even the weight. From that, you will get a show D hardness in the between the range. For example, if you are reinforcing a natural fiber, you will get the hardness, show D hardness about 265 to 70. You will get. If you are reinforcing TI, any other inorganic filler like TIC or like CNT or BN nitride, that boron nitride, so you will get up to 80, maximum 88 to 89 maximum you will get. So that is the range we will get. Then next one is your thermal studies. So thermal property studies, we have 3 different types. So in this case, we are not going to take the thermal conductivity. Why so? Because thermal conductivity will be very less, because these materials can only be used as a insulating materials. For example, epoxy cannot be made as a conductive polymer. If you are going for conducting polymers, it depends upon the polymer should be conductive. and the reinforcement should also be conductive. Then only the testing of thermal conductivity will be useful. So now for this case, if we are using coefficient thermal expansion, so we have two methods. One is and mechanical dilatometer test method. So in thermomechanical analysis method, we have a small piece of zero, that is we can say 5 mm square. So that square has been put on the probe, that with the help of the probe, that using a quartz crystal glass. And what will happen? It will get expanded. But in dilatometer, the dimension of the of that component will be different. Okay, it should be 60 mm maximum. Otherwise, we can say 48 mm to 48 mm length, and the diameter is about 10 mm. Okay. Then thermal degradation process. For thermal degradation process, we are testing TGA. That we can say thermogravimetric analysis. So in TGA, there will be 3 stages. First stage is it will explain what is the evaporation of your sample. It means if you have any small moisture content in that evaporation of moisture will be happen. But in the second stage, that is as well, that Z part, it will say what is the degradation temperature. And the final stage, it will say what is the maximum, what is charge produced in the final stage. But for glass transition temperature, we will get from the DSC scanning, that we can say differential scanning calorimeter. Okay. So now, so these are different types of another test type that is called, we can say, a physical property like density, porosity, water absorption, and contact angle. So density means how after reinforcing the natural fillers, synthetic fillers with the polymers, how your material got reduced, whether it's reduced or it got improved. For example, if you reinforce more natural fillers, what will happen? Your density of the polymer will get reduced. Okay. If you put more, we can say if you put more inorganic filler, why it will get improved? Why? Because when compared to the density of the natural filler with inorganic filler, the inorganic filler having the higher density. Okay, that's why the density of the material will get improved. Then the same porosity, as I already told you, the porosity or the moisture content of, because the fibers of fillers, natural fillers are hydrophilic in nature, whereas the inorganic fillers are hydrophobic in nature. So now we understand why we are adding inorganic filler in order to reduce the porosity of the material. So what does it? Same water absorption, but in contact angle. So how the contact angles be done? So first, the contact angle, a small specimen has been taken with any size, with any dimensional size. Okay, from the syringe, a point, just we can say 6 microliter of water droplet has been dropped on that surface. That angle has been generated with the help of optical microscope. That angle has been calculated. If that angle is less than 90 degree, we can say it's a hydrophilic. If it's more than 90 degree, we can say, and that means more than or equal to 90 degree, we can say it's hydrophobic. So after reinforcing the natural filler with synthetic filler, whether our polymers become hydrophilic or hydrophobic, that we can test on the contact angle measurement. So another property we can say dielectric constant method and dissipation factor method. So in that dielectric property, so we have a setup. In that setup, we can say it's we have to take 1 centimeter square piece. It has been touched with the probe, and electric pulse has been generated. That means frequency has been passed through the sample. Then what will happen? Your dielectric constant will decrease from 100 frequency to 100 hertz frequency to 10 power 6 frequency. That means that's the testing rate. We are going for that, and your dissipation factor also get reducing. So from this dielectric constant, if your frequency with the increasing frequency, if your material get improved, that means dielectric constant improved, means we can be used as this material as for a PCB applications. Okay. Then viscoelastic properties. So viscoelastic properties, it can be happen in we have 3 different methods. First one is in cantilever beam, then dual cantilever beam, then another is a tensile beam, and fourth one we have frictional mode. Okay. So from this, what will happen? We are giving a flexural load or tensile load on the surface of the material by giving a temperature from room to up to 150 degrees Celsius. Why I selected 150 degrees Celsius? Because with the help of our TGA curve, because how we are going to select this one. First that we have to go for TGA. From a TGA, we have to check what is the degradation temperature. From that degradation temperature, according to that only, we are going to select the operating range of the temperature for this viscosity properties. From this, you will get the storage modulus and loss modulus and damping factor. From this, you will get, from damping factor, you will get glass sensor temperature, which is not at all, which cannot be equal to the DSC glass sensor temperature. Okay, and from this lowest storage and loss modulus, what is from this? What is explained that if you go for the same curve will be there. That means due to the higher temperature, the storage modulus and loss modulus will get reduced. How to improve this one? We have to either go for the chemical treatment, otherwise you can go for the reinforcement of the inorganic fillers. So that's why this is one type of even we can, from this conclusion, from that storage and loss modulus, we can say that this type of storage and loss modulus can also be affected with the help of dispersion also, we can say, by plotting a cold plot. Okay. So now what are applications of polymer based nanocomposites? Okay, so now we are seeing, that is, we can say it's different types of applications of polymer based nanocomposites. Okay, so first you can see this we are using in acoustics. So nowadays, so people are saying this is polymer based carbon fiber composites. So nowadays, people are stopped reducing the carbon fiber based nanocomposites instead of using the natural fiber based and inorganic based. But in acoustic application, there is no need for any inorganic based, because inorganic particles are very, very expensive. Okay, so next one is you go to this textile and paper industries. So like this for folders and all, this for making the rollers and all. We are also this application for polymer based nanocomposites. In aerospace and aircraft industry also we have automotive parts. We have the equipments like sports equipment, bicycles, like racket handles. We have we have portable storage sources that also has been fabricated with the help of polymer based nanocomposites. And energy production, like wind turbine blades also has been, because why we are using wind turbine blades in terms of polymer based nanocomposites, because the efficiency will be more compared to the other compared to the conventional carbon fiber based composites. Why is it so? Because the effect of lightweight, the energy production will be more compared to the carbon fiber composites if you are using inorganic filler or natural fiber filler, like that. So another thing is that if you are going for automotive parts, in order to increase the efficiency of the cars. For example, if you nowadays we are switching over to electrical vehicles. So if you are using lightweight application materials by using a polymer based nanocomposites, what will happen? Your efficiency of the electrical vehicle will get improved, and your mileage of that consumption of the fuel cell, that also can be improved. Okay, so these are other different applications of your this polymer based nanocomposites. First one is your for making the tensioning cables, and we can use as storage devices, and we can even use as for electromagnetic interface shielding. Then implants, like in our bone scaffold applications. So that's why we are using nano cellulose based composites with the application, with the reinforcement with graphene and CNT in the form of polymer to get a higher miscent wound, to get a higher mechanical property. Second one, to higher thermal stability. Third, having good we can say good physical properties. And even with this type of composites can also be used for sensors and actuators. So now if you see this car, so nowadays everything has been become in the form of nanocomposites. Okay, so from the starting from the scratch paints on LEDs or non-adhesives. Okay, so everything is completely in the form of nanocomposites. Even the e-transfer applications, like even we can use CNT in the radiators for cooling applications, for enhance the heat transfer coefficient of the radiator. So from this side, I have thank you for giving me this opportunity. And any questions you can ask me now. Hello.
Yes, sir. Dear participants, there is any question?
Any questions?
Dear participants, any other questions from your side? So thank you, Professor, your valuable presentations from the nano composite filler materials. This far more helpful for who are research working in nano composite filler materials. So thank you, sir.
Thank you so much, sir. Somebody asking, check, is it possible to use, what is that?
AG or NU in place of carbon.
Yeah, we can use it. Yeah, we can use it as AG and NU, where it is. Where it means we can gold and silver particles also can be used as a nanoparticle in place of nanoparticles. But what is the application you want to go for that? That is the requirement. So depend upon the application. For example, if we are using silver nanoparticle, it can. So people are mostly using for the thermoconductivity applications. Okay. So if you are using carbon nanoparticles in place of that, I think carbon nanoparticle will be cheaper than the silver one and gold one. So I want to know the application, which application you want to go for this nanoparticles. Okay, sir. Thank you so much for giving me this opportunity. Hope you understood that what are the things I have said. You all.
Yes, sir. Thank you so much, sir.
Thank you so much, sir. Thank you.
So, dear participants, the shared session as per schedule